So before we showed that an even number times an even number is even. Well, is that the same kind of relationship we're going to see with odd? Is an odd number times an odd number odd? Well, first, think of counterexamples, right? Think to yourself, okay, well, let's take some random odd numbers. 1 times 1, that's 1. Okay, that's odd. 1 times 5, that's an odd number. 3 times 5, that's 15. That's going to be an odd number. 7 times 7, 49. That's an odd number. 9 times 5, that's 45. That's an odd number. Okay, so some rudimentary examples showed us that, yeah, this relationship is true. And I can't really think of any counterexamples. This is probably true. So let's try and prove it. First, recognize we're looking at any odd number, any two odd numbers. So we're looking at it for all, or a any proof. So we would say for all a, b that are integers, and we're going to say this is a and this is b. Actually no, we'll go back to the really easy notation. If a and, let's write that bigger, and b are both odd, then a times b is odd. Okay, this is the statement we're going to try and prove. So, what do we need? Well, for this proof, the only word that matters is odd, right? It's the only thing we care about here, so it's the only thing you should know what it means. What is odd? Well, reminding ourselves the definition of odd is going to be any integer x such that it can be written as x is equal to 2k plus 1, where k is an integer. That is the definition you should think of, and that is the definition we're going to use to probably prove this is true. So let's have a look, right? What do we have? We have a for all or a for any. So what are we going to do? First thing we're going to think of is the word let. That's the first thing we're going to write down. Next, we're going to look at our statement and think to ourselves, what's our P that we have to suppose, and what's the Q that we're proving? Well, the statement P is going to be this. And what we're proving is this Q, right? We're saying that if P is true, if A and B are indeed odd, then Q is true, then A times B is odd. Great. So we're going to suppose P. We're going to start by saying let A and B be integers. Let A, B be in the set of integers. Let's write that Z a little nicer. Okay. And A and B be both, some alliteration there, odd. Then let's define what we mean by odd for both of these. Then A is equal to 2m plus 1 and B is equal to 2n plus 1. Okay, fantastic, right? If we're trying to prove that any two of the same odd number multiplied is odd, so if we want to say 7 times 7 or 3 times 3 is always odd, not 7 times 1, because those are two different odd numbers, then you could let this be the same variable, m and m. But no, here I'm doing n, which I understand it can be sometimes hard to hear, but hopefully my writing clears that up. Okay, anyways, moving on. We've supposed our P is true, and we've more rigorously defined what we mean by when they're both odd. Now let's show that when we multiply these two together, we're going to get an odd number, something in the form of x is equal to 2k plus 1. So let's begin. A times B is going to be equal to our A, which is going to be 2m plus 1, multiplied by our B, which is 2n plus 1. Now, based off of this, can we do what we did with the even times odd, where we can just pull something out and get something in this form? And the answer is, I don't see it, right? So what are we left with? Well, maybe we can just expand the brackets and see where we go from there, right? We never know where we're going to go. Sometimes you might try something mathematically and it'll be wrong. You have to go back and think to yourself, well, where else can I go? But here, the only option we really have is to open the bracket. So let's cross multiply. This is going to be equal to 2mn plus 2m plus 2n, so 2m plus 2n, and then 1 times 1 is 1 plus 1. Okay, this looks a lot better. I like it when we have just a plus 1 hanging at the end because that's exactly what our definition for odd is. So what do we do next? We think to ourselves, can we get this as 2 times something, right? It's 2 times some variable k maybe. And it looks like we can because it looks like all of these share a factor of 2. So let's do that. Let's factor out 2. So we're going to get 2 times 2mn plus m plus n, close bracket, plus our 1 on the end here. And there we go. We got it in the form of our odd definition, where this would be our k, this is our x, and we've basically just shown that x is equal to 2 times k plus our 1. There we go. We've shown that this is in fact odd. We've shown that any 2 odd numbers multiplied together is going to give us an odd number. But let's of course make that obvious for the reader and conclude that. Okay. So let's explicitly tell them, hey, 2mn plus m plus n, that's just any integer, right? This could be even, this can be odd. Our definition does not care if k is even or odd. It just cares that k is an integer, and here it must be, right? We're saying 2 integers added, any integers added multiplied is going to be an integer. You're not going to leave that set. So let's write that down, comma, because this is still a sentence. People forget this is still a sentence. We should probably have written then, yada, 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 comma, where 2mn plus m plus n is an integer. There we go. Okay. Now it's time for a very simple conclusion where we say, since a times b is equal to 2 times 2mn plus m plus n plus 1, where 2mn plus m plus n is an integer, then a times b is odd by definition of odd. Great. You don't have to add this by definition of odd part. I'm just doing it because I need to remind you the reason this is true is because it's showing this relationship. It's showing that that relationship is true for this math. Fantastic. You can always define 2mn plus m plus n to be some integer. Like you can say this is equal to k, and then k is in the integers, and then, oh my god, we got the same answer. But why add those extra lines, that extra work, and that extra complexity for the reader? They're going to have to memorize more variables when they're reading it. Like right now we just have 4. We have a, b, m, and n. Why add a 5th one, right? Why make it hard? Awesome. So there we go. We've just proven this.